Välkomna till Kungliga Vetenskapsakademin och den här presskonferensen då vi ska presentera årets Nobelpris i kemi. Welcome to the Royal Swedish Academy of Sciences and this press conference where we will present this year's Nobel Prize in Chemistry. We will keep to our tradition and start in Swedish and then continue in English. And you are of course welcome to ask questions later on in either language. Jag heter Hans Ellegren och är ständig sekreterare här på Kungliga Vetenskapsakademin. Till höger om mig sitter professor Johan Åqvist, ordförande för Nobelkommittén i kemi. Och till vänster om mig professor Heiner Linke, ledamot av Nobelkommittén för kemi och sakkunnig inom ämnet. My name is Hans Ellegren. I'm the Secretary General of the Royal Swedish Academy of Sciences. And to my right is Professor Johan Åqvist, Chair of the Nobel Committee for Chemistry. And to my left is Professor Heiner Linke, member of the Nobel Committee for Chemistry and one of the experts in this field. Årets pris handlar om en grundläggande upptäckt inom nanoteknologin. This year's prize is about a fundamental discovery in nanotechnology. Kungliga Vetenskapsakademin har beslutat att i lika delar utdela 2023 års Nobelpris i kemi till Moungi Bawendi, Massachusetts Institute of Technology, MIT, USA, Brus, Columbia University, USA och Aleksey Yekimov, Nanocrystals Technology Inc, USA, för upptäckt och syntes av kvantprickar. The Royal Swedish Academy of Sciences has decided to award the 2023 Nobel Prize in Chemistry in equal shares to Moungi Bawendi, Massachusetts Institute of Technology, MIT, USA, Brus, Columbia University, USA, and Aleksey Yekimov, Nanocrystals Technology Inc, USA, for the discovery and synthesis of quantum dots. Professor Johan Åqvist will now give us a short summary in English. Please. Thank you.
What you see here in these flasks, ladies and gentlemen, are quantum dots in a liquid solution. Well, you don't actually see them because they are truly tiny. They are what we call nanoparticles, only a few millionths of a millimeter in size. Each particle is a small crystal containing just a couple of thousand atoms. When things become this small, quantum mechanics starts to play all kinds of tricks. The nanoparticles in each flask are made of exactly the same simple substance. So how can they differ in color? Well, that, ladies and gentlemen, is a quantum effect. The particles are so small that their electrons start to get crowded. The smallest quantum dots shine in blue, while the bigger ones shine in yellow and red. They only differ in size, nothing else. And the size changes a lot of their properties, thermal, electric, magnetic, etc. The first observations of this effect were made by two of this year's laureates. Aleksey Yekimov saw it for copper chloride nanoparticles immersed in a glass. And Brus observed it for nanoparticles floating freely in a liquid solution. For a long time, nobody thought you could ever actually make such small particles, but this year's laureates succeeded. However, for quantum dots to become really useful, you needed to be able to make them in solution with exquisite control of their size and surface. Moungi Bawendi invented an ingenious chemical method for doing just this. He could now make perfect nanoparticles of very specific size and very high quality. These achievements represent an important milestone in nanotechnology, and today there are numerous applications of quantum dots ranging from QLED screens to imaging in biochemistry and medicine and much more.
Thank you, Professor Åqvist. And now Professor Heiner Linke will give us a more detailed presentation. Please.
So let me first check the sound works, yes. So the discovery we just saw, and what you also have on the screen, that in the same material, a larger particle can have a red color, a smaller particle can have a blue color, is at its core a quantum mechanical effect. Quantum mechanics predicts that if you take an electron and put it into a small space, the electron's wave function gets compressed. And the smaller you make the space, in this case the particle, the larger the energy of the electron. If you can store more energy in an electron, it can also give more energy to a photon. So the light emitted from a small space, electron in a small space, will be more blue, and that from a larger space will be more red. And this is what you can also see in this animation. So again, if we confine an electron, that's the wave, in a larger particle, it can be more red. But as you compress, imagine making smaller and smaller particles, compressing the wave function more and more, you give the electrons more energy and they send out more blue light. In this sense, quantum dots are a new class of materials. They are different from molecules. If you imagine if you wanted to make different colors with molecules, you would, for each color or for each other property, you would choose a new molecule, a new set of atoms in a new constellation. Quantum dots, however, have all the same structure. They have, in fact, the same structure as a bulk material would have. It's the same atoms in the same constellation, just that a small dot has fewer atoms and a bigger dot has larger atoms. The fact that they then change properties is not only their color, it's essentially every property, every material property you can think of, including electric, optical, magnetic, even catalytic effects, how they influence chemical reaction, even the melting point changes. So in this class of material, you have found a way of changing material properties, not by changing the material, but just by the size. And this is a foundational discovery in nanotechnology, the ability to do this in a controlled manner using quantum mechanical effects. The prediction that this would be possible, now, the prediction that such an effect could occur in theory was made as early as the 1930s. But for the next 5 decades, it seemed near impossible to make such materials because not only do you need perfectly crystalline structures, and you need to control the size exactly, basically atom layer by atom layer, you also need a perfect surface property so that you can get these phenomena and these clear colors. This was not actually expected to be possible. The discovery that this is indeed possible was first made by Aleksey Yekimov, who studied colored glasses. And by adding copper and chlorine to a glass, he was able to show first that the copper chloride formed as nanocrystals, so crystals with crystalline properties. He used deep insight into the physical chemistry to control the size exactly, was then able to show that the color of the glass correlated with the size of the particle, and not just in any way this straight line there means, because the straight line is a smoking gun, that this is a quantum effect. So all of this was done in one sweep of results. The discovery was made a second time in a different context by Brus in the United States, this time for particles in solution, freely in solution, available for further processing. This was done in the context of studying semiconducting particles for their catalytic properties. The vision was, and still is, in fact, to use light, such as solar light, to drive chemical reactions. So it's a form of solar energy conversion. He looked at relatively small particles and again noticed that the optical properties changed with size. This triggered a lot of interest. Just imagine the ability to suddenly be able to tune material properties not only by making new materials but by their size using quantum phenomena is of course very inspiring and triggered a lot of interest to see what could this be used for. But for the next 10 years this was difficult because the size was not quite well controllable enough, the quality was not quite good enough for real applications. Bawendi discovered or invented a method for making these particles in a much more controlled manner. The trick being to precisely control the moment in time when nucleation, the beginning of the particle growth, first changes. So he used a hot solvent, well-chosen solvent, and at one instant suddenly injected the reagents, which led to an instantaneous formation of small embryo crystals, a nucleation event. But then the growth stopped because the solution was diluted and the temperature dropped. Then, by reheating and carefully controlling the temperature, again with deep insight in the growth processes, it's possible to control not only the size, but also keep the size in a very narrow window so that only one size gets produced. And the solvent was chosen such that the surface of the particle was protected and gave a very high quality. This opened then for the possibility of applications. And today we see commercial applications, for example, in TV screens, where quantum dots are used to produce the RGB colors that make up every pixel. We see them in illumination sources, where the LED light, the blue LED light, gets converted into a light that is perceived as pleasant by humans. It's also used widely in biomedical imaging, in this particular example, to visualize the vascular system of a tumor. But this is not where it ends. Research is still very intense, and there is applications expected or being heavily researched in producing photons for quantum communication, for flexible electronics, for sensors, for improving solar cells, making them better or cheaper. And not the least, the same that also Brus had been working on, namely catalysis for solar fuels, among many other things. So for these reasons, the Nobel Prize in Chemistry for 2023 will be awarded to Aleksey Yekimov and Lou Brus for the discovery that it is possible to make such quantum dots, and to Moungi Bawendi for a synthesis method that made quantum dots widely useful.
Thank you, Professor Linke. We shall see now if we have Professor Moungi Bawendi with us on the phone from Cambridge, USA. Are you there, Professor Bawendi?
Yes, I am. I'm here.
Good morning.
Good morning.
I'm very sorry that we had to wake you up in the middle of the night.
Oh, don't be sorry.
Yeah. Please accept our warmest congratulations to receiving the Nobel Prize in Chemistry.
Thank you so much. It's quite an honor.
Yeah. How did you feel learning about this?
Very surprised, sleepy, shocked, unexpected, and very honored.
I understand, yeah. I'm sitting here in the session hall of the Royal Swedish Academy of Sciences at a press conference. There are many interested journalists here from the Swedish and the international press. Are you ready to take some questions from them about your research or your reaction?
Sure.
Okay. Sveriges Television.
Good morning. My name is Thomas von Heiner with Public Service Swedish Television. Something unusual happened this morning in that your names were actually published a few hours early. Did you, by chance, have someone called you already earlier and said something about this, or did you hear about it, or?
No, I didn't know. I was awakened by the Swedish Academy. I was sound asleep. So no, I didn't hear anything about it.
Okay. Yes, please.
Anneli Megner-Arn, Swedish TV4. I didn't quite understand. The smaller the particles were, the higher the energy. But I was just thinking, if you have like just a couple of atoms together, they will sort of have more space if there are few of them. But if there are a large number of particles or atoms, then they would be more crowded together. So how come that smaller particles have higher energy and more towards the blue scale?
Sure. It's really the electron that's created. There's an electron that's created when you shine light, and it's that electron that investigates the space that's available to it. So if you have a very small particle, the space the electron sees is very small. If you have a big particle, the volume that the electron sees is quite large, and so that's how you go from high energy to low energy. The number of atoms defines the volume that's available to that electron.
Okay, please.
David Keaton for the Associated Press. Congratulations on this award. First of all, when was it, sir, that you understood the importance of this discovery and not just its theoretical implications, but also the commercial implications that this could have?
Well, this was a process. I think that the community, because it became a larger community, realized the implications in the mid-90s that there could potentially be some real-world applications.
Please.
Hello, sir. Congratulations. Paul Rees from Al Jazeera English. As a scientist, do you ever have a feeling that you've done work that's so groundbreaking and important that maybe one day you'll get a Nobel Prize, or does it never really cross your mind?
You know, it's a field with a lot of people that have contributed to it over from the beginning. So, no, I didn't think that it would be me that would get this prize. I mean, because we're all working together on this. And yes, I mean, yeah. Please. I didn't think that I would get it.
Yeah, please.
Congratulations, Professor Bawendi. This is Caixin Media from China. I have one question. How do you view the prospect of quantum computing and quantum computers based on quantum dots? Thank you.
This is an area of research, and I don't know what the future holds, and so it'll be very exciting. I think there's still a lot of exciting work to be done in this field. That's for sure.
Please.
I'm Steve Wei from Nordic Chinese Times. Congratulations, Professor. This is a great achievement. The quantum physics is all related to Chen Yang's laws of conservation of party. What's the potential impact do you think this small-size research will have on improving, such as materials science and sustainable applications in the field? Thank you.
I'm not sure I understood the question. I wonder if you can repeat it or rephrase it.
Can you rephrase it and please be very close to the mic?
What is the potential impact do you think this small-size research will have on improving materials science and sustainable applications in the field? Thank you.
So improving something and something sustainable, is that the question? I didn't quite understand.
I think it was a question about the potential applications of the discovery.
Okay. Yes, so they're already widely used as color downshifters, as was already mentioned in the display industry and as biological tags. And there's a lot of work that's still it's heavily researched, other potential applications in photocatalysis and in quantum effects of all sorts. And I think that the world will see in the future where it will go. It's hard to know at the beginning when we're doing this what the exact impact will be, but it's a very exciting area of research, and I'm sure something really interesting is going to come out.
Please.
Yeah, hello, Bogdan Radrejewski, Polish television, TVP Science. I want to ask, because most of us probably heard about quantum dots in regard to the possibility of modifying the color with the size. But as we heard, the potential here is to actually modify literally every properties of such particles simply by changing the size. So what could be the possible prospects of actually using that and changing different things about the particle other than its color itself?
For sure. So you're right. Many properties evolve as you go from the molecular regime of a few atoms to the bulk regime of millions and millions of atoms. And that certainly includes the properties of the surface. And the properties of the surface are properties that could be chemically reactive or photoreactive. And so there's a fair amount of work going on now in looking at photocatalysis using the quantum dots as in some way in that area. There's work looking at using the quantum dots as in flexible electronics, for instance, as carriers of electrons. So yeah, it's not just the colors, but a lot of the electronic properties evolve with the size in ways that could be interesting for applications that some people are already researching, and who knows, other applications may come about through new discoveries.
Mm-hmm. Yeah, please. You have to turn on the mic.
Yeah, congratulations, Professor. And I have a question about the quantum calculation. And do you have any insight about these fields in the future? Thank you.
Yes, well, this is an area that I'm beginning to be quite interested in, and I would say that for the kinds of quantum dots that I work with, it's just the beginning. We're beginning to see that there's a potential there, and we'll just have to pursue it and see where it goes. But it's going to be a process, and we don't know yet.
Okay, this seems to be the last question from the press for you, Professor Bawendi.
Well, thank you very much.
Yeah, thank you very much. And once again, warm congratulations. We look forward to meeting you here in Stockholm in December then.
Me too.
Yeah, see you then.
Quite an honor. Yes, thank you. Bye-bye.
Bye. We shall move on. First, I shall check, do you have a microphone, Professor Åqvist?
No. It's okay.
So let's move on now to more questions about the Chemistry Prize and the research involved. You may want to ask questions to the committee also about their work. Yes? Who was first here? Please.
Hello, this is Caixin Media from China, and mostly the quantum research are mainly focused on physics. So why this year is given to chemistry? Thank you.
Professor Åqvist or
I think
Linke?
I can answer that. The way of making quantum dots, so there's a root of this field in semiconductor physics, I would say. Over many years, similar phenomena had been pursued in semiconductor physics, not at least in the 60s, 70s, when microelectronics was sort of experiencing its first boom. These quantum phenomena that are present, for example, in optoelectronics are confined into structures. They are more about devices than materials. The discovery here is for actually purifying quantum effects to actually become materials you can touch. You can dry these quantum dots. You have powders that are have these new material properties. And the methods of doing this come from chemistry, and in many ways also what you can then continue to do with them, for example, to treat them so that you can use them in biomedical applications, are methods of chemistry. And it's really chemists who have contributed to that field.
Yeah, now.
I wonder how your thoughts went when you decided to give a Russian scientist this award, giving this time with the war in Ukraine to shine the light on Russia and to invite him to the Nobel Prize dinner.
I understand the question. First, we are not involved in the invitation to the Nobel Prize ceremony. That's the Nobel Foundation that does that. When it comes to selecting prize awardees for the Nobel Prize, We simply follow the procedure of identifying the most important discoveries. Having done that, we identify the most important contributors to that finding, those findings, without paying any respect to nationality or any other factors for that meaning. And that means that nationality doesn't matter here, and that's also exactly in accordance with the will of Alfred Nobel, who said that the most worthy person should receive the prize irrespective of nationality. Follow-up?
In your regard, do you think that the scientist should go to the Nobel banquet? Should he be invited to this banquet or not? What's your opinion on that?
We don't have any opinion with that. We work with awarding the most important research, and then the Nobel Foundation is responsible for the ceremony. Yes, please.
Yes, David Keaton from the Associated Press. In the early hours of this morning, the names of the winners and for the prize for which they, the science for which they were awarded was leaked in Swedish media. This was known for about 4 hours now. Would you care to maybe explain how this might have happened and provide sort of, safeguards? What are the safeguards that exist around this, around the prize in general? Thank you.
Let me say that this is, of course, very unfortunate. We deeply regret what happened, for sure. There was a press release sent out for us for still unknown reasons. We have been very active this morning to trying to find out what actually happened, but at this place we don't know that. We deeply regret that this happened. The important thing is that it did not affect the awarding the prize recipients in any way. Nominating and evaluating Nobel Prizes is a very long process that goes on for a very long time. And a decision about the prize is not taken until the Academy has met, and the Academy met this morning. Please.
I'm Sufjan Aksason from Green Post. I also like to ask this procedure question. When you have the recommendation of the Nobel laureates, is one recommendation for these 3 persons, or is many recommendations and you put them together? How this works? Can you answer?
The precise procedures for awarding Nobel Prize recipients is confidential for many different reasons. It will become public 50 years after the decision. That's why we can read about the history of Nobel Prize from 50 years and later. But exactly how the process goes on is confidential. And I can say that a decision is not made until the whole Academy has met, and the Academy met this morning.
But can one recommendation for one person or for many persons?
That we will not comment on exactly what recommendations are made. Maria Günther?
Yes, this is Maria Günther for Dagens Nyheter. When did you contact the laureates? Was it as soon as you learned about the press release, or was it after the decision?
We had no reason to contact anyone until the decision had been made. And the decision was made this morning, and directly after that meeting, which is only a short while ago, then I called the laureates.
Sorry, David Keaton again. Just to clarify, I mean, obviously these names were released in a press release at around 7:30. The meeting took place about 2 hours later. Could you maybe explain, is the meeting just a formal approval of this? Is the sort of decision made in advance, or do you have several suggestions that the committee has to approve, or is it more of a sort of rubber stamp seal of approval for the one that has been chosen by a smaller group of people? Thank you.
The meeting is not just a formality. The Academy as a whole decides about who shall receive the Nobel Prize. That was the case also today. I can again only apologize and regret for that this information was sent out very early. But again, no decision is taken until it's taken. Okay.
Maybe
one more question, yeah?
Yeah. Scientific question. And the size of quantum dots and some fluorescent proteins are similar, so I wonder the differences between them.
So this is correct. Fluorescent proteins are in the same size scale as quantum dots. The mechanism for the fluorescence is then very different. It's really about the molecular states. And in that case of proteins, to change the color, for example, you have to change the structure of the protein, the composition of the sequence. So this is a fundamental difference. And then it's also different materials. Here we're talking about inorganic materials.
Yeah. Thank you for your interest. We hope to see you back here on Monday when we will announce this year's Sveriges Riksbanks Prize in Economical Sciences in the memory of Alfred Nobel.